Given f of x comma y, we want to find the critical points, then determine if there is a minimum, maximum, or saddle point at that location. We'll first find the critical points by determining where the first partial derivatives are both equal to 0 or where either is undefined. Then once we find the critical points, we'll use the second partial derivatives and determine the value of d here. Then based upon the sign of d and the sign of the second partial with respect to x, we can determine whether we have a relative min, relative max, or saddle point at that critical point. Let's begin by determining the first partial derivatives. So for the first partial with respect to x, we'll differentiate with respect to x, treating y as a constant. So the derivative of negative 3 would be 0. The derivative of 7x with respect to x would be 7, plus the derivative of 7x squared with respect to x would be 14x. Then the derivative of 3y with respect to x would be 0, since we're treating y as a constant, and the derivative of 6y squared with respect to x would also be 0. So now we'll find the first partial with respect to y. So now we'll differentiate with respect to y, treating x as a constant. So the derivative of negative 3 would be 0. The derivative of 7x as well as the derivative of 7x squared would both be 0 because we're treating x as a constant. The derivative of 3y with respect to y would be 3, plus the derivative of 6y squared with respect to y would be 12y. And while we're here, let's go ahead and find the second order partial derivatives because we'll need those later. So to find the second order partial derivative with respect to x, we would differentiate f with respect to x twice, or differentiate this partial derivative with respect to x again, which would just give us 14. And then for the second partial with respect to y, we would differentiate f with respect to y twice, treating x as a constant, or just differentiate this partial derivative with respect to y again, which would just be 12. We also need the mixed partial of f with respect to x and then y, so we'll differentiate this partial derivative now with respect to y, which would just be 0. So now to find the critical points, we'll set these two first-order partial derivatives equal to 0 and solve as if it was a system of equations. But notice when we do this, it's really not much of a system because we can easily solve this first equation for x and the second equation for y. And let's go ahead and do this to find the only critical point. If 7 plus 14x equals 0, we would subtract 7 on both sides, giving us 14x equals negative 7. Divide both sides by 14, and we have x equals negative 1/2. And we can easily solve the second equation here for y. 3 plus 12y equals 0. So subtract 3 on both sides. Divide by 12. And we have y equals negative 1/4. So we only have one critical point, which is negative 1/2, comma, negative 1/4. So this is the first part of the question. And now for the second part, we want to determine if there's a minimum, maximum, or saddle point at this location. To do this, we'll use the critical point that we just found and calculate the value of d using this formula here. Notice how this involves the second order partial derivatives, which I've copied over here on the right that we found on the first slide. And notice in this case, because the second order partial derivatives are constants, we actually don't even need the x-coordinate and y-coordinate of the critical point. We have the second order partial with respect to x, which is 14, times the second order partial with respect to y, which is 12, minus the mixed partial squared, which would just be 0 squared. So this is equal to 168. So because d is positive or greater than 0, and also the second partial with respect to x is positive, looking at our list here, this tells us we have a relative minimum at the critical point, negative 1/2, comma, negative 1/4. To verify this, let's look at the graph of the surface in 3D. Here it is. Not only do we have a relative minimum down here, we actually have an absolute minimum, which is why the directions state whether we have a minimum, maximum, or saddle point. So we can say f of x comma y has a minimum at the point negative 1/2 comma negative 1/4. Notice how the question does not ask us for the minimum function value. If we wanted to find the minimum function value, we'd have to evaluate the original function here, f of x comma y, at this critical point. It doesn't ask us to do this, but I did want to point this out. F of negative 1/2 comma negative 1/4 is equal to negative 5.125, which is equal to negative 41/8. So this would be the minimum function value. This information also gives us the point on the surface. Remember, this is a three-dimensional surface, so each point is an ordered triple. So the point would actually be negative 1/2 comma negative 1/4 comma negative 41/8. Again, it doesn't ask us for this information. The only thing we're asked is to indicate if we have a minimum, maximum, or saddle point at the critical point. I hope you found this helpful.